Okay, so this is my demo machine. I'm using VirtualBox, and my target OS is Linux, Ubuntu 64-bit. And in this machine, I also have Vitis 2022.1 and Riviera-PRO 2023.04. All right, so first thing first is let's go ahead and open a terminal here. And let's set up my environment. Then let's go ahead and cd to the directory where the design is located. And again, we're using number 17 here. Okay, so as I mentioned, we're just doing step 7 here, which is to run hardware emulation. Okay, so that's the command to run hardware emulation, and this makefile will launch Riviera-PRO. Okay, so while that's opening, let's rearrange the windows here. Good, there you go. Let's put this over here. All right. Okay, so while Riviera-PRO is running, so what it's actually doing is it's trying to set up the environment with qemu. It's going to compile all of the sources, and it's going to try to simulate. Okay, so there's a compile.do and simulate.do script that were generated by Vitis when you actually make or build the package for hardware emulation. So while this is running, let's go ahead and open compile.do. Compile.do and simulate.do. Okay, so they should be here. All right, so these are the scripts. So compile.do, yeah, so it contains all of the commands to compile the project and link all of the libraries together, and that's generated by default by Vitis. And I didn't change anything here. Okay, and this one here, this is the one that's been generated by Vitis by default. Okay, and let's open it up here so you can see the asym command. Okay, there you go. All right, so this is the asym command here. Okay, so you can see the top level and the libraries and the arguments for the asym command. Okay, so this is the one that's been generated by default. I didn't use it because I wanted to enable advanced data flow. Okay, so let me just close this one here and let me show you guys what I actually used. So this is the one that I used. Okay, so here's the one that's generated by default. I didn't use it. It's commented out. I have one for code coverage, and I have one for advanced data flow. Okay, so the one that I'm using here right now is this one here with advanced data flow enabled, so we can do some debugging later on. So in addition to that, I'm just creating some virtual groups here for each major component of the design. Okay, so that's what it's trying to do right now. Okay, so let me close this one. Okay. All right, and then it's trying to load. So you can see it loaded all of these virtual groups. So once you get this message, just simply run all. Okay. So when you hit that run all, qemu is going to try to boot with the Linux. Okay. So while that's running, what I want to show you guys is the design hierarchy. Okay, so this is the design hierarchy of the of Riviera-PRO. This is the top, and let's just go zoom into it. Okay. So let me just pull this down here. Okay, so I just want to point out, these color-coded icons here. So the ones in orange, these are all SystemC files. Okay, so SIPs is a SystemC, AI engine, a zero instance is SystemC, SIPs NoC is SystemC, and so on. Okay, the green ones are Verilog files. Okay, so systemdpa is a Verilog file. MM2S is a Verilog file, and S2MM as well. And as you remember, these are the auto-generated RTL code from the HLS flow. And the blue ones, the blue icons are the VHDL, okay, VHDL files. And Polar Clip is the user RTL, okay, coded in VHDL. So this is actually the user code, okay? And we'll debug this later on, okay? So this design hierarchy shows all of the instances as part of the design, and you can zoom into it, to see the signals, see the objects, and so on. Okay, so over here, qemu has booted up and Linux is up. So now let's go ahead and try to set this up. So the command is mount cd to this directory here, and then let's go ahead and run. Okay, so what I did there is basically just run the application with the FPGA's device image. So host.exe is the application, and then the XCL bin is the device image, okay, with the bitstream and all of those connectivity there. Okay, so this command there is going to try to run hardware emulation with the software host application being emulated in QEMU, and the AIE, the SystemC generated files from the AIE are now in Riviera-PRO, as you see, and the RTL kernels, the MM2S and S2MM, they are here in Riviera-PRO as well. They're going to be simulated there, and the Polar Clip, as you can see, is going to be simulated in Riviera-PRO as well. Okay. So the test in this tutorial, it's a simple test. They just have a golden vectors set of files. The results will be just compared, to those golden vectors. And it's just going to display either a test pass or a test fail. Okay, so we should get a test passed here. Okay, so in a few seconds now. Should be almost done. There you go. So that's a test passed. Okay. So once we get that, let's just exit QEMU. So basically just hit Control A and then X. So it's going to terminate the connection from QEMU. Okay. So once it's disconnected, now we can start to do some debugging here. Okay. With Riviera-PRO. Okay. So here, let's go ahead and so what I'd like to do in this next part is debug the Polar Clip. Okay, Polar Clip is the user RTL. Okay, so let's focus more on that design. Okay, all right. So here's the Polar Clip here. Here's the virtual group. Okay, and I want to focus the debugging in this in sample T data and out sample T data. Okay, so let's just take a look at this signal here. Let's go ahead and zoom to fit. Okay, and then let's zoom in some more. So this is let's remove this one here. Let's remove this window here. Okay, all right. So let's zoom in some more. Okay, so you can see the different values of the in sample T data here. Okay. So what we could do is actually browse by event. Okay, so browse by event here, and then when you hit the when you change the cursor, it changes from event to event, so you could see when the data changes. Okay, you can also view the delta cycle in the transition there. So here in this transition, there's 3 delta cycles there. What about the next transition? So there's also 3 delta cycles. So you just kind of keep browsing. Okay. Click this again. All right. So it looks like there's about 3 delta cycles that happen during each transition here. So let's remove all of these delta cycles. Okay. Now let's focus our debugging here in the out sample T data. Okay, so let's go ahead and then zoom to fit, and let's go bring the cursor here, and then let's zoom in, zoom into here, that data here. Okay, so okay, yeah, so this is actually a good good place to debug because there's some unknowns here. So let's zoom in here. Okay, so let's see what happens here. So yeah, so there's some unknowns in the signals there, so that's why this bus resulted to an unknown state. Okay. All right. So what we could do again here, let's expand this. Yeah, let's just take a look at the delta cycle again. Now, how many delta cycles? So it looks like there's 11 delta cycles here during this transition. And how about this one? Okay, also 11. Okay. Let's remove all of the delta cycles. Yeah, so you can also trace, during this unknown, you can also click on that and then find the X cost. Okay, so when you click that, it takes you to this window. Let's go ahead and then kind of zoom out a little bit. So these are the different states. This is actually this diamond here. This is where the X value happened, and you can trace back to where that X value propagated from, and these are the times when they happen. Okay, so it's a very good debugging tool. Okay, so we're done with this waveform viewer. Let's close this one. Let me just take your attention to this design hierarchy here. Okay, so in this design hierarchy, again, we are interested in this polar clip. Let's go ahead and find the object, find some objects here. Let's go ahead and find in sample out data, in sample, out sample T data. Okay, so yeah, so that's how you find, yeah, because yeah, these modules will be large, so this is one way to find specific signals with that matches this regular expression here. So this object here, what I would like to see is the drivers and readers for this bus. Okay, so you can see the drivers and readers for that bus. The drivers, this is the line code that drives it, and this is the one of the readers for that bus. So you can actually right click on this one if you want to see the source code. Okay, the process declaration code, and it looks like this goes straight to the polar clip VHDL file and that particular line number there. This is the assignment. And for the reader, you can also show the source. Okay. All right. So that's how you find readers and drivers for a particular object. The next one that I'm going to show is the advanced data flow. Okay. So from here in the design hierarchy, you can actually right click on this one and view the data flow. Okay, so the data flow window is a tool that allows you to explore the connectivity of your design and analyze the data flow between instances. So between instances, concurrent statements, VHDL signals, Verilog nets, and variables. Okay, So the values in the design logic, you can trace that back to their origin and forward to the design outputs. So let's do that. Okay. So this is the polar clip. Yeah. So for example, this one here, if you select that, you can actually expand that to the drivers. Okay. So you can see the drivers of that particular signal, and then you can keep expanding as needed, and you can also view this and discover recursively to see all of the components inside. Okay. Yeah. So it's actually huge. So yeah. So you can see all of the connectivity. Using this data flow window. This polar clip is after all a circuit, so you can see all of the connections between different components inside. Okay. All right. So that's advanced data flow. The next thing I want to show is the code coverage results. Okay. So let's go to this default mode here, or default tab here. Okay. And the code coverage is here. Okay, so let's open HTML. Okay, so that's going to open. So code coverage is a technique that collects the statistics on the execution of each line of HDL code. Okay, so it measures how well your test bench exercises your design. So your test bench in this case is software. Okay. All right. So this one we collected. So this is the overall code coverage. Statement coverage is about 88% covered, and the branch coverage is about 79% covered. Okay. What I want to show you guys is this polar clip, and let's see how much coverage we got from the software. So the polar clip VHDL at 98% statement coverage and 96% branch coverage. Okay, and then you can actually see the source code, okay, over here, and you can see each execution of the line and how many times each line was hit. Okay, so it looks like this particular if statement was hit this many times. Okay, so all of the green ones showing they were hit at least once. If it shows red, that means this particular line wasn't even hit, okay, at all. There's a few more here. Yeah, so this one here wasn't hit, and some of these lines were hit twice. Okay, so this is code coverage. So there's more code coverage capabilities. There's expression coverage, toggle coverage, FSM coverage that you could do with Riviera-PRO. Okay, all right. So that concludes this demo. Okay, so see you guys. Talk to you guys later.